My name is Ria Joe, and today I'm excited to present my work, CHiP-FL, a federated learning framework for equitable ICU risk modeling. The motivation for this project comes from a major challenge in healthcare AI. Clinical data is fragmented across hospitals, but privacy regulations and institutional policies make it difficult to centralize raw patient data. This is especially important in critical care, where risk models need diverse, multi institutional data to generalize well. Federated learning offers a promising solution. Instead of moving patient data into one shared database, each hospital trains locally and sends model updates to a central coordinator. The coordinator aggregates those updates into a shared model while raw data stays local. But in healthcare, hospitals are not identical clients. They differ in size, patient acuity, missingness patterns, lab ordering habits, documentation, and clinical workflows. A large academic medical center may have thousands of ICU stays, while a smaller community hospital may have fewer cases and very different patient distributions. In machine learning, this is called non IID data, but in healthcare, it reflects real institutional differences. Standard federated learning methods can allow larger hospitals to dominate training. As a result, a model may achieve high global AUROC while performing unevenly across institutions. The model looks strong overall, but smaller hospitals may receive less reliable predictive tools. So the central question of this project is, can we design a federated learning algorithm that maintains strong predictive performance while distributing benefit more equitably across hospitals? To address this, I developed CHiP-FL, which stands for Client Clustering, Hierarchical Aggregation, and Personalization Federated Learning. The core idea is to handle hospital heterogeneity at three levels: global, cluster, and local. First, CHiP-FL uses clustering. Each hospital is represented by a data signature vector containing sample size, label prevalence, missingness structure, and summary statistics of key vitals and labs. Hospitals with similar signatures are grouped using k-means clustering. Second, CHiP-FL uses hierarchical aggregation. Updates are first aggregated within hospital clusters, and then those cluster models are aggregated into a global model. This preserves meaningful differences between groups of hospitals while still allowing global knowledge sharing. Third, CHiP-FL includes personalization. After federated training, each hospital can fine tune from its cluster model using only its own private data. So instead of forcing every hospital into one global average, CHiP-FL allows hospitals to learn from the whole federation, learn more strongly from similar peers, and still adapt locally. For evaluation, I used the eICU Collaborative Research Database, a public multi-center ICU dataset with over 200,000 de-identified ICU admissions from 208 hospital units across the US. Each hospital unit was treated as one federated client, and the prediction task was in-hospital mortality. Features were extracted from clinical domains, including vitals, labs, medications, diagnoses, and care plan indicators, for example, heart rate, oxygen saturation, lactate, vasopressors, sepsis, ventilation, and dialysis. The cohort was restricted to adults, and discharge status strings were excluded to prevent label leakage. Missing values were retained with explicit missingness indicators because in healthcare, the absence of a measurement can itself carry clinical information. All methods were implemented using Flower and trained with federated logistic regression. I chose logistic regression because the goal was not to maximize deep learning performance, but to compare how different federated optimization strategies affect institutional equity. I compared CHiP-FL against several baselines: Fed average, Fed prox, personalization, hierarchical aggregation, and cluster training without global aggregation. A key part of this project is that I did not only evaluate mean AUROC. Global AUROC can hide unequal performance across hospitals. So, I also measured worst decile AUROC, which captures performance among the lowest performing hospitals, Gini coefficient, which measures inequality across sites, standard deviation of hospital AUROC, and size bias, which measures whether model performance systematically depends on hospital size. The results show a clear trade-off. FedProx achieved the highest mean AUROC of around 0.933, however, it also had the highest standard deviation and a strong size bias of around negative 0.032, suggesting that its gains were not evenly distributed across hospitals. In contrast, CHiP-FL achieved competitive mean AUROC of around 0.903 for the global model and 0.897 after personalization, but its major advantage was equity. CHiP-FL nearly eliminated size-dependent performance bias, reducing the size bias slope to about negative 0.0023 globally and negative 0.0019 after personalization. That represents over a 90% reduction in institutional size bias compared with FedProx. This is the central finding. CHiP-FL does not maximize raw global AUROC, but it dramatically reduces the relationship between hospital size and predictive benefit. The Pareto frontier analysis reinforces this. Different federated learning algorithms occupy different regions of a performance equity space. FedProx represents the performance extreme. Hierarchical aggregation gives strong worst decile protection but lower global performance. Fed average reduces dispersion but still preserves size bias. CHiP-FL occupies a structurally fair region by maintaining competitive performance while nearly eliminating institutional scale bias. For translational medicine, this matters because clinical AI systems need to work across diverse care settings, not only at the largest academic hospitals. If federated learning mainly benefits large institutions, then it may reinforce the inequities it is meant to solve. CHiP-FL reframes federated learning as a structural coordination problem. Hospitals are connected but not identical. Some hospitals are similar to each other, and each hospital still has local characteristics that matter. This work has several limitations. It used logistic regression rather than deep neural networks, clusters were fixed rather than adaptive, the experiment was simulated using eICU rather than deployed in a live federation, and results reflect a single random seed. Future work should explore adaptive clustering, deep learning extensions, patient-level fairness, and prospective evaluation in real federated clinical frameworks. To conclude, CHiP-FL shows that healthcare federated learning should not be evaluated only by global predictive accuracy. We should also ask who benefits from the model, which hospitals are left behind, and does performance depend on institutional scale. By combining client clustering, hierarchical aggregation, and personalization, CHiP-FL achieves competitive ICU mortality prediction while reducing hospital size dependent performance bias by over 90%. The main takeaway is that equitable healthcare AI requires fairness to be built directly into federated optimization, not added afterward. Thank you so much, and I am happy to take any questions, so feel free to reach out.